Okay, so we are in Generalized Linear Models with examples in R. We're just in Chapter 2 here, and we are on question 2.15. Okay, so here's the question. So an experiment was conducted to determine how to maximize Mermaid meadowfoam flower production. And there's a table in 2.9, which I've reproduced right here. For extraction as vegetable oil. I don't know what any of that means, to be honest, but we can still do our analysis on it. So we'll get to these questions kind of piecemeal here, one at a time. But the first thing that we need to do is we need to get the flowers data set up on our machine. So I'm going to install the GLM's data package and load it. And I'm going to call forward the flowers data set, which is part of this package. And then I'm going to assign it the label D just so that I can reduce some typing. So let this load. And I've called the structure of D so we can see what it looks like. So it's a data frame with 24 rows and 3 variables. So we have flowers, which looks to be, so we're going to find out later that this is actually the average of 10 observations. Okay. We have light, which I believe that this is wavelengths of light, and we have timing. So light is being delivered at two different times, which are labeled before and PFI. Okay. So the first question is we want to plot flowers against light intensity, distinguishing the two timings. Okay. So to do this, let me rerun that. So first I'm going to plot flowers against light as we're supposed to, and I'm going to just take this part of my data where timing equals before, right? Because we're supposed to distinguish the two timings. And then I'm going to come back and manually add the points where the timing is PFI and color those red and give it a different marker. Okay, so there's that. I believe we're supposed to comment for this. So I think generally we can find a trend where for both timing categories that flowers is decreasing as light increases. And it looks that at any given level of light, flowers is less for the PFI condition as compared to the before condition. Okay. So moving on now to parts 2 and 3. So we are going to create models with a systemic component where we have 2 main effects, light and timing. Okay. And then another one where we have light times timing. Okay, so I'll talk about both of these. And in both instances, we are meant to discuss what such a systematic component what does that imply about the relationship between the variables. Okay, so first we'll look at flowers being regressed on light plus timing. Okay, so this would imply that flowers, the outcome variable, is just modeled by an additive relationship between light and timing. That's all. Pretty basic. But how does that differ then from the next one, where we have light asterisk timing? Okay. So hopefully you are familiar with this. But in R, if you write a model such as this, where you're separating variables not by a plus but by an asterisk, then what this is doing is it will take light, or one of the variables, plus the next variable, timing, plus the interaction between them. And so the interaction would look like this: light, timing, and its beta coefficient here. Okay, so what does this imply about the relationship between the variables? So if we use this model, well, this model implies that we think that flowers can be modeled as not simply an additive relationship with light and timing, but that also flowers has an interact or that we need this interaction term. In other words, that part of explaining the outcome of flowers requires that we assume that light has a different relationship with flowers for the two different timings. I'm sorry if that is a little bit hard to follow, but that's kind of the treachery of interactions. I shouldn't say treachery as though it's a bad thing, but they can be a little bit difficult to explain, interpret sometimes. So, but as we go on, hopefully this becomes a little bit more evident. Okay, so now we're going to create two models. Well, we're not going to create them. We're going to implement the two models that we just discussed in R, and then talk about which one is preferred. Okay. So before I do this, well, so here's the code. You can see the code. And before I do this, I'm going to guess which one is going to be preferred. Okay. So I'm looking at these two. I'm looking at the data here. Okay. And I notice that really the data looks very, very similar. So if I look at the slope of the red dots, it looks very similar to the slope of the open dots. Okay, now remember the different type of dot is representing the different timing conditions. Okay, and I also notice that the red dots are typically below the open dots. And so to me, this suggests that that the better model is going to be the non-interaction model. If an interaction was important, we would expect the slopes of the red and the empty dots to differ, and they don't. Okay, and so so in this case, I'm going to guess that the better model is going to be the non-interaction one. Okay, so I'm defining my two models here. Okay, and I'm going to look at the summaries. But the summary isn't going to really tell us which one is preferred necessarily, and so we could quote unquote find the preferred one in a lot of different ways. But what I'm going to do is just use the AIC metric. And again, remember with AIC, we're looking for the lower value. The lower value is better. Okay. So I run this. Okay. So let's go all the way here to the bottom to the AIC scores. All right. And we see that the first model, the one without an interaction, is lower, and that makes it better, okay, which is what we predicted. Now, it also, remember, part of the reason that I predicted that the red would be better than the open dots, or I'm sorry, that the interaction would be, that the interaction model would be not as good as the non-interaction model, was because the red and the empty dots have a similar slope, or they, by my eye, they do. I don't know that analytically, but they seem to. If an interaction was important, then it would mean that for any particular level of light, or for any particular level of light, or how do I want to say this? That the slopes would differ for the two timing conditions across light. So, and I did not see that, and so I did not think that that the interaction term was going to be useful. Okay, and indeed, the AIC bears that out. But also, if I look at the summaries and we look at the interaction for the if we look at the interaction term for the second model, we see that it's basically 0 and it has an incredibly high p-value, suggesting that it's not important. Okay. All right. Next, part 5. The fitted model should use all prior weights as 10. What difference does it make if the prior weights are not defined, which in other words defaults to all of the weights being 1? Okay. So when I was going through this, I was a little taken aback because I didn't really understand that there was prior weights in this. But really, I should not have been surprised because when I looked at the structure of the data, number of flowers was this decimal, but we can't really have decimals. We can't have fractions of flowers. And so what I should have done, and what you should do, is to make sure that you read the, why can't I do that? Give me a second. Okay, so what we should do is read the help file for flowers, and unfortunately, for reasons that I don't understand, even though it was working earlier, that command is not working, but there's no reason that it should not work on your machine. But you should type in $flowers, which is the name of the data set, and you'll find that the variable flowers is the mean number of flowers averaged over 10 different seedlings. Okay, this is just taken right from the help file. Okay. So that means, well, so one thing that we could do is to weight each of the observations then, and we can do that in R with this weights command here. Okay. So now I have my previous model, which was M1. So I'm going to rerun the model, the simpler model without the interaction, because that seems to be better. I'm going to run it. I've already ran it without the weights, but now I have weights. Okay. And we'll compare the outcomes here. All right. And they are identical. Okay. You can go through and compare them, but we shouldn't be surprised that they're identical, because when every observation is weighted the same, then what would it mean to weight them in the first place, right? We haven't changed anything by adding the weight of 10, as opposed to, by default, having them all weighted as 1. Okay. Second to last part 6. So we want to plot the systematic components of our preferred regression model. Okay, so again, the preferred one, I think, is just where we have light plus timing without the interaction. Okay, so I'm just plotting what the plot you've already seen with the points. Okay, and then I'm just adding lines to the 2 timing conditions here, right? The black dotted line for the open black circles, which was the timing before, timing equals before, and then the red line for timing equals RFI. Okay. So finally, interpret the model. Okay. So I guess the way that I would, I'm not really sure what it means to interpret the model. Are we supposed to interpret the outcome, or it's not really clear? But I think that the interpretation is that number of flowers, or the average number of flowers, decreases with light intensity, okay, and that the timing matters such that timing RFI generally suppresses, constitutively suppresses flowers compared to the before timing condition. Okay. All right, that is it for this one.